let's have a look at running a hyper-efficient serverless platform on top of Azure Kubernetes Service. First, we're gonna dive into this by looking at some pain points that all of us face with Kubernetes and serverless compute as you may know it today. From an application developer's point of view, it's hard to do workload right-sizing, which means identifying and assigning the right resource requests and limits for our containers. Additionally, it's really complicated to do demand-based downscaling, which is scaling containers efficiently depending on the demand they are facing. Both application developers and platform administrators struggle with bin packing, which means providing the right amount of resources at a certain point in time. And this is especially hard when we think about serverless scenarios where we strive for fast, efficient horizontal scaling of many workloads. Containers and well-known serverless platforms have a problem with cold start times. Different I/O constraints make us wait for the underlying platform or the container to become ready and invoke our custom code, which means scaling down to zero is almost impossible. If we look at containers in particular, they consist of different layers providing everything required by our app to work as expected. Distribution, instantiation, and scaling is also slow because of those additional layers. Last but not least, we tend to over-provision containers to deal with different load patterns. No matter if those load patterns are predictable or not, due to the constraints mentioned before, we keep a considerable amount of containers running in order to respond to incoming load as fast as possible. Addressing all those concerns would allow us to run more workloads, consume less resources, drive overall resource utilization, and scale efficiently down to zero without having to care about cold start times anymore. And this is where WebAssembly comes into play. WebAssembly is portable, meaning we compile code once and run it on any operating system or CPU architecture. Especially compared to containers, WebAssembly workloads are tiny. The strict sandbox execution model of WebAssembly prevents user code from accessing underlying system resources by default. Again, compared to containers, WebAssembly eliminates the dilemma of cold start times. WebAssembly modules have a cold start time of less than a millisecond. By using Spin, the developer tool for building serverless WebAssembly workloads, we can build applications using different programming languages. Those Spin apps are executed using triggers, like for example an incoming HTTP request. In contrast to serverless functions running in containers, every trigger invocation results in a clean instantiation and invocation of the Spin app. Due to cold start times being less than a millisecond, this has almost no impact on end-to-end response times. However, it allows us to scale down to zero. You can run Spin apps everywhere. You can run them locally in our hosted service Fermyon Cloud or on top of Kubernetes using either open source SpinKube or Fermyon Platform for Kubernetes. And that's what we will dive into now. For comparison reasons, we'll look at a lab setup with 3 different AKS clusters. For every scenario, we provisioned a dedicated yet identical AKS cluster. We took latest Azure functions and deployed unique workloads on the first cluster. The second cluster has open source SpinKube deployed to it, and it will run unique Spin apps. The third cluster has Fermyon Platform for Kubernetes deployed and will also run unique Spin apps. From a benchmarking point of view, we wanted to deploy as many workloads as possible to those clusters to strive for high density. Obviously, we want to ensure both workloads and the underlying AKS cluster remain healthy. To simulate load, we sent 20,000 requests to random workloads running on the particular cluster every 10 minutes. The load testing client itself is executed from within each cluster to prevent surrounding cloud infrastructure or Kubernetes components such as ingress controllers from affecting the benchmark results. With that, let's have a quick look at our AKS clusters. Okay, so first let's have a look at the Azure portal. Over here, we are looking at the list of all our Kubernetes clusters in Azure. Please note, every cluster is running Kubernetes version 1.28.5, is deployed to Germany West Central, and has features like virtual nodes disabled. That being said, let's move to the terminal and let's have a look at our cluster responsible for running containerized workloads. So we have deployed Azure functions in containers into the app's namespace. A unique functions app results in a unique pod being executed on that cluster, so we can simply count those pods and spot that 30 workloads are running on this particular cluster. Let's double check the node utilization using ktop nodes, and as we can see, we're using just 6% of the overall CPU resources and 81% of the available memory resources. Final step over here is to check if we're not facing any kind of load test. And nope, the last load test iteration is already completed and a couple of minutes old, meaning that those values that we get reported by ktop nodes represent the current utilization that is not facing any kind of load. Let's move back to the Azure portal. So every Kubernetes cluster reports metrics to Azure Monitor, and we have deployed Azure Managed Grafana into this subscription, giving us nice dashboards to dive into those metrics. So we can see our containers cluster again over here using roughly 12% CPU and 68% of memory, and you can spot the load test iterations over here, there, and there. Please also note that the load test client is obviously also consuming some resources in teal blue over here. However, we can see 30 workloads being executed on this AKS cluster, and the interesting thing is, no matter if those container deployments were idle or under pressure, we consume a high amount of memory also during idle time. I would say this one is roughly about 7.5 gigabytes of memory to run 30 workloads. That being said, let's move back to our terminal. Let's clean that one and let's move to the second Kubernetes cluster. This cluster has open source SpinKube deployed on top of it. SpinKube allows you to run WebAssembly workloads next to your containerized applications. How that works in detail will we see in a second. But first, let's talk about the developer experience. Developers can use all the goodness from Spin to craft their serverless WebAssembly workloads. You can start by using one of our templates, or you can roll your own templates. I've already created a Spin app using the HTTP Go template, and what I want to do next is I want to set a local variable so that I don't have to type the name of the OCI artifact again and again. So Spin packages and distributes apps as OCI artifacts, meaning you can distribute your Spin apps through Azure Container Registry. So let's do that. Let's use Spin registry push, provide the name of our OCI artifact, also specify --build to ensure that the app is compiled down to WebAssembly before pushing it to Azure Container Registry. So this is now my code being compiled down to the 𝗦𝗲𝗀𝗶𝗁 platform, packaged as OCI artifact and submitted to Azure Container Registry. So with that in place, we can use SpinKube scaffold, again specify for which OCI artifact, and we end up with a Kubernetes deployment manifest, right? So you can use whatever tool you want to deploy this manifest into your Kubernetes cluster, right? You can use kubectl, you can use GitOps, you can use Helm. Whatever works for you works for SpinKube. When you deploy a Spin app into your cluster, the Spin operator takes care of creating and managing the underlying Kubernetes primitives. So if you deploy a Spin app like this to a Kubernetes cluster, a corresponding pod will be created. However, if we look at the Spin apps, we can see that every Spin app has an executor specified pointing to containerd shim for Spin. So instead of spawning a regular container, SpinKube uses containerd shim for Spin to run the WebAssembly module and count the number of workloads again by counting the number of pods in the app's namespace, and we see that this cluster is able to run 135 workloads. Let's have a look at the overall node utilization again, and we can see that we are currently consuming 32% CPUs and 57% of memory. Let's check if a load test is currently running. No, there was a load test running recently. It is roughly 2 minutes old, right? They usually run for 90 seconds or so. So maybe the metrics that we saw from the metrics API, like CPU and memory utilization, still reflect the load tests. But to be on the safe side, let's move over to Grafana and have a look at the SpinKube utilization. We see 25.6% CPU utilization and 48.3% memory utilization. Again, you know, there's a slight difference in how recent those values are. So it will take a couple of seconds to reflect that the load test is already finished. But we can spike all the load test iterations over here and over there. In teal blue, we can see CPU allocation by the default namespace, which hosts our load test client. On top of that, we can also see kubesystem allocating a little bit more in contrast to our Azure Functions in Containers example. And this is because we are running 135 workloads in contrast to just 30 workloads. If we take a look at the overall memory consumption down here, we can see that we on average have a maximum of roughly about 4 gigabytes when it comes to memory utilization. And in that time, we see numbers dropping again because right now more recent metrics are populated through Azure Monitor and find their way into our Grafana dashboard. So we expect those numbers to go down even further. To be on the safe side, let's quickly refresh it once again, and we see the chart going down. All right, with that, let's go back to the terminal. Let's clean this thing up and change to the third cluster. This cluster has Fermyon Platform for Kubernetes deployed on top of it. In contrast to SpinKube, Fermyon Platform for Kubernetes is using a different execution model, allowing you to run a high-density serverless platform on your Kubernetes cluster. And in this case, it is a single node AKS. From a developer's perspective, nothing changes. You can still use all the goodness from Spin to craft your serverless WebAssembly workloads, and you can still use OCI artifacts to package and distribute your apps through registries like Azure Container Registry. And at this point, you can again use your preferred tool to deploy your Kubernetes manifests into your cluster. Fermyon Platform for Kubernetes takes care of the instance of Spin app, and instead of spawning Kubernetes primitives like pods, things are treated differently. Fermyon Platform for Kubernetes recognizes your intent to run a new app. It downloads the OCI artifact, and then it takes care of internally loading, caching, instantiating, and invoking the Spin app if the corresponding trigger asks the platform to run your code. We still end up with Spin apps in that cluster. However, you can see the app identifiers being way higher than in our SpinKube lab. This time we're using the Fermyon Platform specific executor. However, as there are no pods and there is no apps namespace, right, we can't simply count the pods to see how many workloads we are currently running. Instead, I have a secondary terminal running over here, doing a pod forwarding to the admin service from Fermyon Platform for Kubernetes. We can use a simple curl to ask the platform, hey, how many workloads are currently running on that single node AKS cluster? And we get back incredible 3,504 workloads being executed right now. Right? Due to the different application lifecycle of serverless WebAssembly workloads, Fermyon Platform for Kubernetes can instantiate a particular app as soon as a request hits Fermyon Platform for Kubernetes. So let's have a look at the overall node utilization using K-top nodes again. We can see that we're using 16% CPU and 69% memory to run over 3,500 apps. Again, let's check if we are currently doing some load tests. No, the last load test iteration is already completed and is roughly about 5.5 minutes old. So let's move over to Grafana and have a look at those numbers as well. And as you can see, we have CPU utilization around 22.5%, memory utilization under 40%. We can spot the load tests, and we can also spot the default namespace. This is where the load test client runs, allocating resources. And the interesting thing over here is that we have a max memory utilization of under 4 GB, again, to run 3,500 apps on a single node Kubernetes cluster. Okay, now let's dive into those observations. From a high-level point of view, we can increase density using WebAssembly, especially with Fermyon Platform for Kubernetes, which allows us to run thousands of workloads on a single node Kubernetes cluster. SpinKube and Fermyon Platform for Kubernetes bring even better response time compared to containers. Also, from a financial point of view, we can go from $7.76 per containerized workload down to amazing 6 cents per workload due to the high density provided by Fermyon Platform for Kubernetes. Besides testing performance and reliability in lab environments, we pair with different organizations like, for example, 𝗫 to run real-world workloads using Spin and WebAssembly on AKS. 𝗫 was able to cut down costs by roughly 60% without trading off performance. If you want to learn more about Spin, SpinKube, or Fermyon Platform for Kubernetes, check out these resources and find us at the Fermyon booth.